期中考试 ASD， 都大多心碎了。这东西是有一些作业，
All right, we will go ahead and get started. So welcome to the 22nd session of EE 7391. So I have, in this case, don't go to me, I have something that I'm handing out, which is the next homework. It's kind of getting us to sort of the final stages as I went. I want the microphone to be muted. All right, the final stages of this, let's go ahead and show you this. This is assignment number 6. Assigned today, due Monday, November 19th. So it's due not next week, but the week after, that first Monday. That's the Monday before our Thanksgiving break. We will have class that day. I will have another assignment that we'll actually hand out on that day as well. This one has 4 problems. Actually, it's important that you use this as your cover sheet because actually the problem that you're solving, 6-1, you actually solve here. The answer is here. I kind of made it easier because this is a convolution problem. And it's actually entering in values into this thing. So it just made it easier, rather than having you recreate this guy, to use that as a table. Same thing with the pooling stuff. There's some things that we're doing with pooling. We'll talk about pooling today. Get those ideas out here. Your output image goes there, and then it gives you instructions where you put X's here. So you're doing those things here. The rest of it is just more or less instructions. There is, though, a computing assignment. This is actually, in this case, a classification of one-dimensional signals using a convolutional neural network. So you're going to be writing or building a convolutional neural network in MATLAB to do this, writing the code. It's not too bad, though, because it is fairly straightforward because it's one-dimensional signals, not 2D signals. And we're actually using, as it turns out, stride convolution, as it's called. So you kind of, there's less to keep track of. That's really what it comes down to in terms of doing this. This cost function is actually one that showed up previously in a previous homework set. This turns out to actually be like a cross-entropy loss function, but with binary ±1 signals, which is kind of nice because it then makes the signals, if you will, zero mean. That turns out to be useful, and as has been found. So this is kind of a way to do that. But basically, you're building the algorithm off of that. But what you have is you have signals that are either impulsive or tonal. And so, if you will, you've got a set of signals, and you've got these matrices. Now, I did notice one typo here, which I'm going to fix. X of t, an 18 by n training signal matrix, where each column contains a signal to be classified. So the way to think of it is this X of t is basically a matrix where the X of t here is 18 samples, and then it's by n, where n is 1,000. And so this one corresponds to sort of the vector x1, right? That's what that means. And it's 18 samples long. So the way to think of it is it's a time series, right? It's a signal that's 18 samples long. And if you start looking at these, if you take these and you plot them out, so if you plot these out, you'll see that they tend to look either like that, or, that is for n, sorry, actually, let's say this n is 1, this is 1, let's call this t. They look either like that, or they kind of look like that, right? But there's some noise added and so on. So the point is, it either is a tone or it's a click. That's the way to think of it. Of course, it's only 18 samples long, so it's kind of hard to listen to. That's pretty short. The reason I made them short is so that, again, your code runs fast, right, or runs faster. If I made this seconds long, and that would just, slow down the code, as it were. You don't need many samples to be able to classify this. But that is, if you will, I'm calling it X of t because it's training. And then for each one of these, I've got also a Y. I've got a Y, which is like this. And again, this is not going in the notes, so you might want to take notes if you need it. This is your vector Y of t, and this, of course, has Y of 1. This is either 1 or -1, depending upon what type of signal it is. So it's just a binary classification problem. And of course, you have 1,000 of those. So that's your classification. Now, what I decided to do is explicitly divide these two things up. So you got your training signal and you got your training labels. And then I have a testing signal, or a testing data set, which is half the length. And I just noticed I need to put in a half there, 0.5n. Of course, it's right in your data. This is the validation set. So you run your algorithm, you train with this, but then you can use this to compute an error to see how you validate, as it were. And this is sort of 2/3, 1/3, the way to think of it. where you have 1,500 samples. We kind of divide it up that way. And so you're asked to plot this and then implement a 2-layer convolutive neural network. And the thing is, it's going to have P output channels. We're going to talk about output channels today, where each channel employs one-dimensional convolution with 2-sample decimation. And that's stride convolution with a spacing of 2. That's the way to think of it. And again, we'll talk about that today. There's actually one thing I didn't talk about that. That is the filter length is, you can make that filter length equal to 5 samples. So you can write that down as well. And then the second layer, you use tangent. So it's not really that deep of a network, as it were. It's only 2 layers. But the first layer is convolutive. And then the second layer is fully connected, and then you perform the adaptation, and you basically build the system, adapt it, and then essentially see how well it performs in terms of classification. So that's the task for this. Now, like I said, this will take some time, so I did make this worth what? What is it? 55 points out of the 100, so it's a big chunk. So definitely want to dive into it and start looking at it, seeing the difficulties. It will take some time to code up. It's not necessarily straightforward to do all the things. We're going to talk about several of these things today, so you get an idea of the kinds of things that you want to do. But that's the homework. As I said, it's due on the 19th, and then we're going to have one homework after this as well, and that homework is going to deal with sort of ancillary issues in machine learning, because this is the most important one. The convolutional neural network, I would say, gets used for most problems in this space. But we're also going to talk about PCA and ICA in that homework. Any questions on this? Any initial questions? Yes?
Yeah, Professor, in this design, it seems that W have 25 filters in this design. You choose 25 filters to...
Oh, you're talking about this first one?
Yeah.
Oh, the first one. Well, I mean, take a look at it. It's actually a 3x3 convolution kernel filtering a 5x5 input image to produce a 3x3 output image.
Yeah.
So in fact, a 5x5 input image has 25 pixels, right?
Yeah, but I mean in the first page.
Yeah. So let me explain. Yeah. These are pixels. And this is your matrix W that would correspond to a multiply of a vector to produce a vector.
Yeah.
Does that make sense?
Yeah. So each column can be seen as one filter.
No.
Each
column could be seen as one pixel.
Oh, okay.
Right? That's the way to think of it. Think of these as the actual pixels. Maybe the way to think about this, so maybe I'll talk about this. It'll take some time. And by the way, I've got it up as well on the course webpage. This is basically 6.1 in the problem set. What you have is you have an image, which we'll call this image, script X. And it's 5x5. It's basically 5 columns, 5 rows, right? So it's got 25, it's literally this, right? That. Each one of those is a pixel. And what you do is you do 2-dimensional convolution with a W, which in this case is 3x3, and that produces what we're going to call a D hat. Now the question is, what's the size of the D hat? I just realized I want to do something here. What's the size? Well, you have some choices, but if you allow only valid convolutions, this is actually very important. This is one of the things I want to talk about today. Anyway, what you want to do is you want to take this and put it here, and then start putting it over this piece. And that, multiplied by all those values, summed together, will be the first element of the image. And then you move it over. By the way, we'll mark that red. And then you move it over. You move it over to, say, this position. Move it over there. And that's going to create that pixel. And then you move it over one more time. And by the way, what's happening when you move it over? You multiply the weights in this by the values underneath it, sum it all together. That's what a 2-dimensional convolution is, right? And then you move it over one more time to there, and you get it here, and you get that pixel. And that's all you can do. The next one is you're going to move it down. In this case, you're going to move it down to there, and that'll give you the next pixel, right? And so on. And guess what? That builds a 3x3, right? That builds a 3 by 3. How many pixels here? 25. How many pixels here? 9. That is what you see here. 25 pixels, 9 pixels. The way to think of it is this thing contains the W. So what I claim is take the pixels in X, stack them into a long vector. There exists a W which has, in this case, 81 non-zero entries that contain this guy, that when you multiply the vector by this matrix, you produce another vector that, if you rearrange, is that image I just said. So does that make sense?
Yeah.
So the entries of this guy are actually these values, somewhere interspersed, right? Copied. There's places where you got zeros too. Basically, this is the playing out of the thing I ended the last lecture with. Take a look at the last lecture at the very end. We talked about one-dimensional signals. You could have these, these Toeplitz matrices. But with 2D signals, it's different. So what I need you to do is actually take a look at the math and try to write it down and say, oh yeah, to construct the right thing here, I need to put the values in certain places. To construct the right thing here, I need to put the values in certain places, and so on, right? Yes?
You said only valid convolutions or something like that. So why can't we zero pad and then make it 25?
We could. We could actually zero pad and do that. That is a design choice if you wanted to do it. The main reason, though, why we generally don't zero pad, or you want to be careful about zero padding, is it doesn't help you to recognize a pixel at the edge of an image, right? In other words, what does it mean to have a pixel right next to an edge of an image? Well, technically, that pixel, the zeros next to that pixel aren't real. And if I'm using something that's trying to use this sort of shift invariance idea, I don't want to have that happen in my image, right? So in some sense, it doesn't make sense to apply, zero padding in this problem, despite the fact that you could do it, because it starts generating outputs that look anomalous, right? I start recognizing things that are interesting because they're on the edge of the image, and I don't want that. So that's kind of the reason why the tendency is to use what's called valid convolutions, which are only convolutions that would be non-zero for everything. Non-zero weights, non-zero input samples to produce non-zero outputs. So what that means is that the data shrinks, right? As I process things get smaller and smaller and smaller. Is there a question? You just, okay, so I wasn't sure. So that's what generally happens is in this context. So yeah, yes?
So do we need to do exact convolution, or could we do a close correlation? Because you know that.
Oh yeah, convolution versus correlation. Right. So the question is, actually, what you're doing is correlation. You're effectively, you don't have to do the time reversal. I mean, so again, traditional folks would say, and this is true, you would say, okay, a convolution is you flip and you flip, right? You flip in the X and you flip in the Y, and then you drag it around. You don't have to do that. You could treat it as a correlation. And that's one thing that the folks in this field of convolutional neural networks and basic machine learning in general don't worry about the flipping to make the indices go. They basically just, like I said, they treat that as a template. By the way, in image processing, it's also the case. People tend not to be too concerned about, the flipping business. They basically say, okay, apply this to my image and drag it around. I don't have to flip it in either direction. It makes the indexing easier. All right, any other immediate questions? Because I want to jump into the material. But this is actually one thing I wanted to talk about, which is, notice that in 2D and also 1D convolutions, sort of valid regions of outputs cause basically data samples to be reduced, right? Reduced from input to output. So the idea here is, we get smaller, right? We're getting smaller from 5 to 3. Our Y, if this is our X, our Y that's coming out is actually a smaller image. And that, and that could be a concern if I'm, kind of running into this scenario where I don't want to get things to be too small. But actually, that's actually something that's good for me in a sense, because I don't want my data necessarily to grow. And this actually leads to another issue with convolutional neural networks that, again, we're going to talk about later in this lecture. Let's talk about convolutional neural networks. Convolutional neural networks. And by the way, most systems these days that are attacking, sort of structured problems with sensor data use convolutional neural networks. They're basically multi-layer. So what are they? They're multi-layer neural networks with one or more convolutional layers at the, if you will, or sort towards, maybe that's the right way to say it, because it's not necessarily always at the input, it's towards the input. And what that means is obviously near the front. So the idea, and by the way, why do we have them? They're useful for data that has either time or spatial shifts that don't affect performance. In fact, I want to ignore them. They should be ignored, right? In other words, if I say, here is an object, I'm taking a picture, and it's an object of something, and you say, okay, I want to recognize that object. It's not like suddenly you move it over to the right, and it's a different object. It's the same object. So the idea here is I want to use processing that in some sense takes into account shifts. Well, the way you do that is you essentially constrain the weights of the network so that shifts are in some sense part of the structure. That's what a convolutional layer is. It's basically a structure that has shifts in it. It has this sort of allows signals. It produces outputs that are kind of shifted versions of the inputs, but with the same weights at every point. So the same weights apply to every position in the image or in the time domain signal. So that kind of makes sense. If you want to ignore shifts, then you want to build signals. Of course, you'll make patterns that have spatial structure, but the weights that you're training are independent of that spatial structure, right? Does that make sense? That's where you're taking out the spatial nature of it. You're imposing it on the system, not on the data. And of course, the data itself is going to get passed through, or is going to get produced. And in fact, generally, I should say, each layer has few coefficients. And this is due to weight sharing. But has, if you will, nearly the same number of outputs as inputs per channel. This is ignoring this valid regions issue that we just talked about, right? The valid regions issue is sort of the edges. So, if I have a very large image and I do a convolution, then the output of the convolution for that image is roughly the same as the input. So I don't really shrink down the number of samples. And this actually leads to a problem. This leads to an issue that we have to take care of. But it kind of shows you the overall structure. What we do is we have some sort of input pattern. And I'm going to denote that input pattern as a vector. Even though it's a vector, it has a 1D structure or a 2D structure, just like I mentioned in the homework. And that goes into a convolutional layer, conv layer 1. And of course this has weights. But remember, the weights are small. The number of weights I have, if it's a 1D, then the weights I have, let's talk about that. It is basically, you can think of it as a vector Wi of k for each channel I. right? So if I were 1, then what I would have out here would be sort of a y1n, which is basically the same size as x of n. Okay? Now, by the way, if it's 2D, then what I have is what I'm going to call WIK. This is actually this 2D pattern, right? Like 3 by 3 for each channel I. So, you know, in this case, if I have this can be thought of as an impulse response. Gosh, in optics, this has a name too. I'm trying to remember it. If any optics folks can help me. It's like a point spread function. PSF, that's it. Point spread function. Point spread function, right? That's what we would call it if we wanted to call it a signal processing thing. Right? Because you take a point, it spreads out that way, that's what it looks like. Okay, this is with 3 by 3, it could be 5 by 5, it could be 4 by 4. I mean, you have a choice there. 7 by 7 is an example, I've seen that too. I mean, but generally it's square, it tends to be square. And this produces an output. Okay, that's good. And it does it by convolution. Notice that this is small. This is nowhere near, I mean, let's go back to the homework. You got 9 coefficients for 25 samples, right? That's small, right? For all those 25 samples to produce 9 out. Now, let's say this image wasn't 5 by 5. Let's say it was 20 by 20. Well, that would be 400 samples. I'd still have 9 coefficients. So small number of coefficients to take, 400 samples in, if it's 20 by 20, and produce, slightly less than 400 out. So really constrained in the coefficient space, which is good. That's what I want to do. But you might think, well, where do I get the richness, right? Where is it that I can actually get the system to actually do what I want? Well, I can have multiple channels. So the way to think of it is this y1 of n could actually have multiple channels in it. It could have, if you will, and I say yi of k, it could have sort of a y11, a y12, a y13, and so on, down to y1, and we'll say p for the number of channels. And these are vectors, okay? Right? It could be that big if this was p multiple channels. So now I have this long vector, and now what am I going to do? I'm going to send it into another convolutional layer. Conv layer 2. What does the conv layer 2 do? Well, actually, it could have this could have pi inputs and po outputs, each of which has wij of k, right, for each input output. You get the idea? So now, here's a 3 by 3, but let's say I have, I don't know, 3 outputs, 3 images that are produced here. This might generate 9 images. I might have a 3 by 3, 3 outputs for every input. That's typically what happens. That's what people tend to do, is they actually tend to increase the number of channels here. Now again, 3 inputs, 9 outputs, the number of coefficients I have is going to be, it's going to be pi times po times 3 times 3, right? So that's the number of coefficients I have. So it'll still be small, but it's going to grow, right? The number of coefficients are going to grow. Yes?
So when you say multiple outputs per layer, is it like, what changes? Like, is it the way the weights get applied for, because
yeah, you're saying in this convolutional layer, how do I do it?
Yes.
Yeah, so the weight, I mean, there's a couple of different ways to visualize it. Trying to think, one way to think about it is kind of, we'll use this NIPS paper, right? What happens is you take this input, and what you end up doing is you end up generating, say, 4 outputs from it, like this, right? And the way to think of this is these 4 outputs are the result of 4 different convolutions. Now, here I have, from this layer to this layer, I have 4 in to 4 out. That's actually 4 by 4 channels. That's actually 16 sets of coefficients, right? Because I'm not just mapping this to that to that. That's silly. I want to get mixing again, right? To get the mixing that I want, what I want to do is add those together, combine those, combine that, combine that. So I want to sort of like 4 to 1, 4 to 1. But I need a convolution here, convolution there, convolution there, convolution there. So I have 4 convolutions, and then I have that 4 times. I have 16 convolutions I'm doing. Make sense? So that's how that works out in terms of this. And what that's then doing is, here we went from 1 to 4. We went from, in this case, 4 to 4, so we didn't grow the numbers. But you can kind of see, in this architecture, they went from 4 to 12. So they went 4 to 12. So in this case, it's 4 inputs, 12 outputs. So that's 48 filters. And you're saying, okay, well, this starts to get more complicated. Yeah, they want to have some filters that will differentiate some things. Okay, that's the idea behind this, to be able to differentiate these things. But notice, though, that they got smaller. Okay? And you might ask the question, well, how is it that you actually get smaller? Because that's an important factor of this. By the way, you can see the problem if you don't get smaller, right? I mean, right now, if you go back just to this issue, I have a convolutional layer in. If I have P channels, I get, P, basically for one image, I get P images. And that's P, here. And I take those P images, I now have P squared images here, right? There's going to be sort of on the order of PIPO images here. So that's going to be a lot of pixels, right? If I don't do something. So that's the concern as you do this. By the way, at some point in this process, and it might be 1 layer, it might be 2 layer, it might be, 19 layers, I think, is one of the architectures, or hundreds of layers. I mean, there is someone that did 1,000 layers. Okay, let's just do that. Right? Kind of crazy, but obviously someone with a lot of computational time and a lot of resources, right? At some point, what you do is you treat this layer as a single vector. This has a term. This is called flattening. Flattening. And the idea here is, okay, I'm kind of flatten the layer. I'm kind of no longer thinking about the layer as an image. I'm thinking of it just as a vector. And at that point, I think, oh yeah, what am I doing? Well, if I have 10 classes, then I'm doing sort of the mapping from this to that, and I'm doing the standard weighted sum. This particular layer is going to have many coefficients, right? And this type of layer has a name too. This layer is called a fully connected layer. So, and it's going to behave like we've been talking about. We've been saying that's basically a matrix. We'll call that W3. That's a standard matrix that you would see applied to the input vector to produce the output vector. You're used to that, okay? And there might be 1 or more of these. If there's only 1 of these, then this would produce some set of outputs like, if you will, a yn of k, which we're trying to make like our yn, which is our, classification vector or whatever we're trying to do. That's what ends up happening with respect to this, okay? So this is how the system is constructed. 1 or more, and typically more than 1, convolutional layers, followed by a flattening layer, and then 1 or more fully connected layers to get to the output, which then you're going to do your j of k cost function on to be able to do the computation. So that's how this all works out. If you will, what this does, this structure reduces the number of parameters needed at the initial layers and this leads to basically a constrained system that, due to convolution, works on shift input signals. That is, you can take the resulting structure, if it's an image, move it to the left, move it to the right, and the system still works. It's been trained in a way to deal with that. That's the way to think of it. Okay? And you might say, well, wait a second, we didn't send in shifting images. We never trained it with images that were shifted. And you're right, you didn't. You constrained the structure so that shifting was allowed. Does that make sense? That's the advantage of this. That's the reason why this is so useful. And why do we have shift input signals? Because we like taking pictures. We like recording sounds. Speech is a shift input signal. The fact that I say something later doesn't make it different. The fact that I say something later doesn't make it different, right? I repeat myself, it's the same information. And when you wait a little bit to talk to your audio recognition device that you have in your home, it's the same way. It doesn't say, oh, shoot, could you go back and shift your signals? It says, okay, I'm okay. You say your words and shifting is fine. So that's the reason why this has such power. So it reduces the number of parameters, which is one thing, and it works on shift input signals, which is another thing. So two benefits from this, okay? And the only drawback is that it's a little harder to code, okay? And by the way, everyone's experienced this. That's one of the reasons why people say, oh, let me go find a framework that has this. Let me go find some software that someone's already built. And the reason it's harder to code is because if you look at it, it's easy to deal with matrices, but it's harder to keep track of all of the places where you got common signals, common coefficients. Because eventually when you compute gradients, you want to sum up all those corresponding derivatives that come from those particular positions, of course. And the other thing is you want to take advantage of all the zeros in this guy, so you don't want to just use it as a matrix. You want to use it actually as a convolution to save the resulting time associated with that effort. But like I said, so that's one of the reasons why the structure tends to get reused. It's one of these things where people say, yeah, let me build a system that kind of uses this overall structure, and then I can make it work for me and do good things. Now, let's talk about sort of the data growth, because it tends to happen. Like I said, if you build a system that has convolutions in it, you actually run into the problem that although the number of coefficients is small, right, here's the number of coefficients, the number of data doesn't shrink. And if I go to multiple channels, then I'm actually generating new images, new feature images from this. So I want to do something. What I want to do is very simple. I want to reduce the size of the images over here. I want to make them smaller, because eventually if I have lots of different images, I could actually make them, if you will, lower resolution, and I'll still have the information in them, okay? Signal processing engineers know what to do. It's a simple thing. It's called decimation, okay? One of the issues is when cascading convolutional layers, the number of samples, the number of output samples tends to grow. And you might say it doesn't have to. I mean, you could have just a single channel, but the problem is that's not how the brain works. It's not like, in other words, you want to expand the number of channels in the structure somewhat. All right? That is, you don't want to just have a single filter followed by produce one image and then followed by, maybe a nonlinearity, and then take that one image, filter it again, nonlinearity. I mean, you can kind of already see that's not going to get you much richness, right? You're just going to take that one image and keep on transforming it into a new image. It's not going to turn into something that's somehow special. What you want to do is start creating features from that image. So you want to create multiple images from one. And of course, that leads you to multiple channels, which leads you to multiple channels, which tends to grow the number of pixels that you have. And so basically, we desire a way to reduce the number of samples. Okay? The simplest way, always talk about the simplest, is basically to decimate. So the idea here is decimate is simply take every, qth sample, where q is some integer. Say q is 2, you take every 2 samples, q is 3, you take every 3 samples. The idea here is if I have an image, and we'll go ahead and make it even number in this case. So I have a 6 by 6 image, right? It's a 6 by 6. If I take every, and I say q is equal to 2, then this would take this pixel and that pixel and that one, that one, that one, that one, that one, that one, that one. That would then, via decimation, produce a 3 by 3. So good way to reduce the size of an image, right? Now, obviously, I'm losing something, right? I'm losing information because I've gotten rid of, in this case, 3. This reduces, a number of pixels by the ratio of 1 over q squared, right? So that could be significant. So I don't want to lose that. So people when they thought about this, they thought, oh yeah, I could do clever things here. And this leads to the concept which is called pooling, which is a structured and actually data adaptive decimation of either time or shift input signals. And there's actually multiple types. But before I get to that, let's go ahead and pause. We're actually at a good pausing point now. So we'll pause here, take a short break, be back at 5:46.
Professor?
Yes.
I'm not quite understand. In this question,
Yes.
the input image is 6 by 6.
Correct.
And when you do the pooling, max pooling for 2 by 2 pattern, then how come the
No. There's two things that are being asked. Read the problem all the way through. You're actually being asked two things. You're being asked, you actually should draw your image here, which will be smaller. You're responsible for the size. And then this shows you where the gradient updates happen. So this relates back to this original image as to what positions have been selected.
Oh, okay.
Yeah, we're gonna talk about that. Yeah, because we have gradients to calculate, right? Yeah. That's one of the things. So we got to know where the pixels came from. Yes. Sure.
If this is a 5 by 5 image,
Uh-huh.
and actually have 3 channels.
Oh no, I didn't say. Well, all right. Go ahead. Yeah.
That it will create 3 more 3.
Correct. So it'll be 27 pixels.
So, and if there is a flake layer, for example,
Yeah.
what will this layer do? It will put this 27.
It just into one. It just makes a 27 element. The way to think of it, I mean, there's two ways to view it. If you store everything as a vector, but just know where the boundaries are, then flattening just says, forget about the convolutional structure. I'm going to have a fully, a full W, right?
So for this, for the size of this flake layer is
27 by 1. You got it. That's what it would be. Yep. Exactly. Yeah. Sure.
只能填9个数，你剩下空的全部填0。是不填。
不是 D 这个是9个的这种。
我知道，但是你每一个 D 是由9个成绩组成，那剩下的呢？就不写了。
不写。
搞得好奇异啊！本来我挺清楚的。
什么奇异？
就是本来那个算那个 D 就是这样长加长叠加。
他把那个成成一列，或者展成一列。
他问题是他把整个 x 展成这样，展成这样以后，你写的时候它就不是个方阵。
对，他是把那个图25个 pixel 展成一行，然后那9个 coefficient 展成一个，这样的去。
你这样写下来，其实它就相当于岔开了就。
对，就是这样。
All right, we'll go ahead and jump back into it. So, what I wanted to do is talk about this issue of pooling, which is basically, again, from a signal processing perspective, it's just decimation. It's just taking signals and making smaller numbers of samples from those signals by throwing some samples out. But we have to do it in a clever way. That's the thing. We don't want to just simply, well, I should say, if we do it in a clever way, we might get better performance. But it's interesting that because the system is adaptive, there's somewhat still of a debate that you don't need to be clever. You could just decimate because guess what? There's a filter before this decimator and there's a filter after this decimator, and they're all getting adapted. So maybe it's learning around any choice that you might make, right, in terms of the resulting decimation. But having said that, there are some conventions that people use to do this. And so let's talk about the different methods of pooling. Perhaps the most popular method of pooling is called max pooling, which is basically to say for a local neighborhood, basically you can think of it as Q by Q neighborhood, find the largest value and basically send to the output or send to the output image. So that's the idea. So here what you would do is rather than take, what I just did here, right? I just took the 6 by 6, copy, rather than take this guy and, oh, there it was. It's up there. Paste. Rather than take this guy and take every sample, what I do is I actually start looking at these values. And I say, okay, let me take a look at some of these values. Of course, now I'm getting rid of some of my lines. Let me go ahead and take a look at some of these values. I guess I added too many. Hold on a second. 1, 2, 4. We'll get rid of this one, I guess. All right. Rather than actually taking these values, what I'm going to do is I'm going to say, which one of these 4 is the maximum? If this guy is the max of all 4, then send this one to the output. So this gets sent to the output here, right? And then let me look now, and now here's the thing. I can also then move to the next position. And I could do this, and again, I need another integer. I could do this one r samples away. R might be Q. It doesn't have to be. But let's say R, if essentially Q is 2 and R is 2, then what I'm going to do is I'm going to move over to this position, 2 over, and maybe now that's the largest one. So that's the one that gets copied over. Does that make sense? So I'm actually copying different ones. I'm not doing just a normal sampling. I'm doing a data-dependent sampling now. And then I move over one more, and of course I'm moving over here, and this guy I'm here, and maybe now that's the one that's the largest. Well, that's the one I get. So you end up getting these values at different points. Now, I know you're saying, I mean, one question you might have is, why max? Don't know. There's actually not really, I mean, people will say, let's use maximum. One thing I will say, though, if I'm using ReLUs, then obviously there's information in the positive stuff, right? So maximum kind of preserves that. The other thing that's kind of interesting or beneficial is, and you'll see this, if you use ReLUs and you use max pooling, then you can swap those operations because the maximum over a set is the same whether you use ReLUs or not, because ReLUs a monotonically non-decreasing function. So it's not going to change the sorting. You can actually do some, if you will, optimization there if you wanted to. But, you know, this is actually still somewhat of an open issue. I would claim that this is not necessarily set in stone. This is what everyone should use. But it turns out it's what people tend to use. Okay? Yes, there was a question?
Would you have issues if the data is periodic, like say?
Yeah. You're saying if the data is periodic, this is not reconstructing the data. And the answer is yeah. The goal is not to reconstruct the data. That's the funny thing. The problem is not to somehow preserve the quality of the input data and the output. I mean, you're going to lose something, right? You're going to lose something by decimating. The thinking here is we try to lose as little as possible by decimating. And doing this adaptive, data-dependent decimation might do that. But it's very different from the traditional view of decimation and signal processing, which is preserve, preserve, preserve. You know, I'm trying to preserve whatever information is there. I may not be, right? I might be selectively trying to isolate information that's important to me. So that's the reason why the design rules here are kind of important, and if you will, aren't as well specified as in the context of sampling theory, which is well trodden in the in the EE space. Here it's adaptive, so the fact that you can do adaptive stuff means that you have some freedom. But it is important to keep track of where these locations are. In this process, you must keep track of where the samples came from. For training, that is, when I do training, I have to do backprop. And I have to figure out which pixel is which so I can then figure out what position that corresponds to for my coefficients so I can do the right calculations. So I need to actually keep track of where these values came from in terms of their positions, that is positions. So that's something that you have to keep track of in this process. That's the reason why I have you homework assignment where you actually do that. You're actually indicating where those are, so I recognize that you recognize where those are. Now, it actually then leads to an additional kind of issue of when you're doing the backpropagation, keeping track of those positions so you can do the gradient calculations. Fortunately, in your homework, I'm not having you do the max pooling, you're just doing decimation. So it's very regular, okay, as to what you're doing. So that's relatively straightforward from the standpoint of keeping track of stuff. But this is just one type of pooling. There's max pooling. There's something called average pooling. What is average pooling? Just take the average of the values. That's right. Average pooling, which is you know what? My thing's not behaving. Take a local average of all Q by Q pixels in neighborhood and send to output image, you know. So this I'm not going to do, but the idea, I mean, I'm not going to show you. The idea there is I'm going to take this image and I'm going to start taking those 4 values, you know, sum them together, divide by 4, put that at the output. Sum this together, divide by 4, put it at the output, okay? What that's going to mean is you now note that all input pixels are used to compute outputs after pooling. And that implies that all positions in the input appear at the output, right? Effectively. That is, when I compute gradients, all of the positions are going to correspond to things at the output. So I'm actually going to have gradient calculations affecting all positions at the input, okay? And in fact, it's relatively straightforward. What ends up happening is whatever my gradient is for that local area, I'm going to end up then multiplying it, you know, spreading it to 4 values, and then using it 4 times, right? Divided by 4, you know, in the case of Q equal to 2. If it's Q 3 by 3, it would be 9. I'd have 9 positions. But you get the idea. For an image, I have to keep track of that and actually indicate. And I say appear, I say depend. You know, this is really dependence. Because that's important for me for gradients. So average pooling is another way to do it. Okay, what's another way to do it? Well, there's L2 pooling, which would be basically you essentially treat the local you know, Q by Q image as a vector. Local Q by Q pixel neighborhood as a Euclidean vector. As a Euclidean vector, and then what you do is you basically say the output pixel is equal to the norm of this neighborhood, right? The squared norm. Sorry, it's not actually the square root. It's the square root of the sum of the squares. So you don't do squaring. You actually do the square root of the sum of the squares, right? So whatever the input vector is, this local patch, I guess it's a D. It's generally a D. Well, no, I guess it's a Y. It's going to be some portion of a Y that you're going to do this for. You're going to take those 4 pixels, put them in a vector, 1, 2, 3, 4, and take, you know, square each one, sum them together, take the square root, right? So this is going to take squaring, and then take the square root. So that's your output pixel. So you do that. And again, that's going to basically be like this. Same dependence as average pooling. Okay? And there may be other pooling methods. I don't want to go into any, I mean, people start coming up with different methods, different adaptive methods. You know, again, there's been sort of generation of ideas here without, it's not so clear that it's critical that you do this. Max pooling tends to be useful just because, you know, it actually, one thing it does, max pooling and the decimation, you know, basically reduces the number of gradients you have to compute. So that's useful. Average pooling is more complicated because you have to compute more gradients or at least use more values. And so that tends to involve more work. But, you know, you need this because what this allows you to do is then have in your structure, you would have an input, you would have a conv layer 1, and this would now have some, and by the way, this might have, if it's a color image, it might have 3 inputs. And now this is going to have some number of outputs at channel 1. Each one of them is an image. And then you have another conv layer, 2. And this is going to have P2. Again, some number, and generally these are going to grow. Well, guess what? We could do pooling. Pooling layer. This will now reduce sample count by 1 over q squared, right? So what happens is the number of samples in terms of the number of values is going up until I pool, and then it goes down. And then I could have another conv layer and so on. This will continue on. All right, what does this end up looking like? Well, let's take a look at, actually this is a very important paper. Actually here. ImageNet classification with deep convolutional neural networks. Where did I find it? Actually, I did a search to find it. It's cited by 30,000 people. Okay, so a lot of people have looked at this, right? What is it? It's basically a description of a neural network architecture that was applied to a 1.2 million high-resolution image data set in the ImageNet contest. 1,000 different classes. So nice big problem that people looked at, these folks. And of course, you know, what's interesting is this guy is on the original backprop paper, right? The 1986 chapter, right? That's where he is. Anyway, here's what the architecture looks like. It's kind of interesting. You can actually see it. Notice you've got these images. These are 224 by 224, so no downsampling, no decimation, by 3, it's color image. They then go to 48 channels. 48 channels, and they actually go to, in this case, same size image, right? The same size. Actually, you know, some of this is getting cut off. That kind of bugs me. 11 by 11, 11 by 11. I'm not sure what this is up here. Well, the point is that you have 48 different channels here associated with this. And then you do a 5 by 5 size. This is the size of the image channel. There's a max pooling layer here. So 55 becomes 27. So here's the shrinking of the image. Here's the number of channels. 48 channels goes to 128. Another max pooling. 27 by 27 becomes 13. 192. Right, 192, and then they do 128, and this is all 13 by 13. Then dense. They basically do max pooling here, flattening, then they do this to get to 1,000. So you're looking at this saying, well, yeah, it looks like there's, if you will, stride of 4 here. These are this is a 5 by 5 kernel, a 3 by 3 kernel, and so on, all the way down. It has many, many, if you will, 256 kernels of size 5 by 5 of 48. Actually, 256 kernels is the number of kernels. The 5 by 5, that's right, it's 5 by 5 is the image. 48's the input. 256 is the output. And so we're kind of, you know, if you will, going kind of, if you will, think of this as the input dimension, 48 by 256. That's the number of input channels, number of output channels. So that's the way to think of it. You end up getting these huge numbers of, if you will, neurons, many, many, many channels, okay? Why is this useful? Because when you do this, going back up to this, you can create a system which has a top 5 error rate, that is, your answer falls in the top 5 listing, 17% across 1,000 classes, which was actually better, considerably better than the previous state of the art. So they're able basically to start achieving classification on these very hard problems, very large data sets, with this sort of structure. And what you're doing here is, again, and notice it's all architecture, right? Basically, you know, they say we've got a data set that's not ours, the architecture, that's what we design. What's the algorithm? Backprop. So they really are using the original algorithm, they're just applying this architecture. Okay, so they have a ReLU nonlinearity associated with this. And of course they have to map it to GPUs to make the computation happen in a reasonable amount of time, especially back in 2012. But you know, basically that's what they're doing, and they're able to achieve these kinds of results, right? Dalmatian comes out first. Mushroom comes out, right? You're able to actually get these sorts of classifications. Again, the listing, the possible topics here are thousands, or 1,000 topics, right? So it is pretty impressive that they're able to do this type of thing with different types of images that obviously are shifted with respect to each other and so on. So this is how you create these systems that have this overall richness, right? And this is what actually led people. But by the way, the same basic concepts are still in this original paper, right? This one that came from the 90s, right? Where, granted it wasn't as rich. We're only talking about, 10 categories rather than 1,000. But, the basic ideas were actually described here. So they're just expanding them to these overall areas. That's really where the innovation has come. Questions about this? At least initial questions about this? Like I said, we're not coding up this type of problem. We're not doing image processing. We're doing one-dimensional type of processing. But the same concepts show up in the 1D case as well, and show up as well as in speech recognition. So speech recognition is also moved this way, where you end up taking the time domain stuff and turning it into these filters that you're then layering on top of each other. All right. What I want to do now, if we start the topic, is talk about another very important, so we've talked about kind of the important features associated with these algorithms. We've talked about, if you will, in ConvNets, we have the issue of layered structures. We have the issue of downsampling or decimation. Which, of course, this layered structures leads to fewer parameters. And if you will, more constrained systems. And constrained systems. Decimation, this allows, reasonable computation. Actually, reasonable computation and storage. Because if we don't do this, then we basically explode the number of samples that we have to record. So we do this as well. There's actually a third thing which really has to do with algorithmic issue, which is how to choose a good step size for each layer. And, we know that we've already seen the idea. There is the initialization. Right? We talked about initialization. This keeps sort of weight values. It starts weight values. Or starting weight values are good for initial convergence. Right? And we saw the example. We talked about this. This is Glorot, He. These are the two papers I mentioned. And, they're good for initial convergence, but it is possible that weights grow, right? Weights change to cause basically, layers to be large or small in amplitude, right? Signal layers. And this, of course, is going to cause problems for gradient descent. I know if my signal layers become too large, I have to lower the step size. If my signal layers become too small, I have to increase the step size. And the layers before my current layers are driving how much gain I have at the at the current layer. So I have this issue. So it seems like I need to do something. And of course, we know what to do. In adaptive filters, we use normalized LMS. And this solves problems, right? Basically, our mu of n is like a mu naught over length x of n squared, okay? Plus some beta. And we do that, and that kind of solves all problems. If the input signal grows, no problem. Still stable. Everything works. What is it that we need to do for neural networks? Well, relatively recent paper. Batch normalization. 2015. Accelerating deep network training by reducing internal covariance shift. Okay. Really, it should be that because there are even papers that are claiming this isn't what the algorithm's doing. So that's kind of, we're new enough with these ideas that really this should just be called accelerating deep network training because that's what they did. What did they do? They did kind of a normalized step size, but not just a normalized step size, as it turns out. They did something actually a little more clever, but it's funny, they kind of recognized the idea that, you know, here, since the full whitening, by the way, they actually started out by talking about whitening, about decorrelating the input signal, which actually is making the signal IID. We already know IID is good for convergence, right? Because it means all the eigenvalues are 1, so, you know, the bowl's round. So they understand this. This comes from this idea. Covariance, if we make this diagonal, we're good. Here's the transformation that does it. We know how to do it. That's all good. But they say, you know what? We're not even going to do that. We're just going to normalize out the input signal by subtracting its mean, making it 0 mean. Ah, we know that's good too. And reducing the variance, right? Making the variance of this 1. So make it 0 mean, unit variance. Now all the data looks like this. But here's the problem. I don't want to do this. This is going to be different for every pattern, right? And it's going to be different across batches of patterns. And there's another problem, which is that normalizing the layer would change what the layer does because there's nonlinearities past it. So what they recognized is you need to normalize the data for training, but then you need to build back the original scale that you took out by multiplying by gamma and adding a beta. So do this for the training part, but then build another set, another pair of parameters that's going to return your original x back to y. So this yk looks like the original xk if gamma is, you know, square root of the variance and beta is the mean. Now I know you're saying, well, it seems like you're just putting back the original, you know, the original data. No, what you end up doing is changing the process where now your weights of your layer are driven by this signal. And we're going to actually use training to estimate gamma and beta. So we're going to add 2 parameters. So the way to think of it is there is a gain and an offset associated with every signal now that we're now going to adapt. And now our weights, if you will, don't have to deal with scaling or shifting. They can just adapt to be different, i.e. to make the patterns look somewhat different, right? That's the basic idea. So they go through the process of saying, okay, I'm going to, and by the way, they do this over what's called a mini batch. So maybe I should make the mention of what a mini batch is. This is, you know, small issue, but we need to actually mention it. Mini batch, which is essentially to treat a small amount of data as the entire data set. And the way to think of it is it's like a block size smaller than n. What's n? N's the number of patterns, right? Number of training pairs. So if I have 1,000 training pairs, it n's 1,000. Well, I could say, let me just treat the first 100, and I'll treat that like a block, and I'll train off of that. Okay? Another way to view this, think of LMS as a mini batch of one sample, right? So the idea here is you're kind of averaging over, not an LMS, you don't average, you just take one sample. A mini batch would be to take a data set which was some fraction of the total number of samples, just train over that. So it's kind of like an averaged gradient. It's not a true steepest descent direction. It's actually like a local averaging of a bunch of gradients, but it's not going to LMS where the mini batch would be 1. So it's going somewhere between 1 and n. That's the idea. Okay, that was just a sidelight. Just want you to be aware of what the terminology means. We understand this basic idea as sort of gradient averaging. But what we're doing here is we're going to have these statistics that we're going to compute over the mini batch, okay? And we actually are going to use these guys. The way to think of them is this is the transformation that we're going to do, okay? Where, if you will, this is the mean, this is the variance, this is how data hat gets changed because we have to change it. So this is computed off statistics, and then this ends up being the resulting change that I want. Now, where does this enter into the algorithm? Well, what I need to do in the algorithm is actually be able to compute gradients off of these quantities. So this L here is the loss function that you're optimizing for. What I need to know in this sort of isolated issue of inserting this change is what are the gradients associated with some of these guys when I have a loss function, because I need to be able to propagate the errors through these resulting calculations. These are calculations I'm doing. If I have a gradient, I got to have my gradient pass through these calculations. So I have these. So the question is, how are the gradients computed? Well, it's pretty straightforward, actually. If you go back to the original equations, so I'll show you what one of these looks like, because you have a similar one that you're doing. If you're going back to these original equations, okay, if I look at, let's look at x hat of I. X hat of I depends upon x, which is just a sample, no gradient. Depends upon mu b, and it depends upon sigma b squared, right? Sigma b squared has this dependence. Okay. If I'm looking at the change in, let's see, actually, where's my x? If I'm looking at the change in my loss, so let's talk about this. If I'm looking at the change in my loss with respect to, actually, let's do a change. Let's do the loss function, the derivative of the loss with respect to gamma. Let's start with that one. That's probably the easiest one to deal with. Then, if I look at my gamma, I have one gamma for all my y's, right? So that means the change in the loss is going to depend upon all the different values that I have with respect to the derivative with respect to y, and then all the different changes with respect to xi hat. So the fact that gamma is common for all of these means that this ends up being the sum, I from 1 to m, because I have m of those, of the derivative of the loss with respect to y, times, in this case, the derivative, basically the way to think of it is the derivative of y with respect to x hat. Sorry, derivative of y with respect to gamma, right? And the derivative of y with respect to gamma is just x hat. So this guy gets replaced with, right? This guy replaced with x hat, xi hat. So that's what that ends up being, that total that derivative here, that partial derivative with respect to this. So that's what you get here. All right, I'm out of time. I gotta continue this maybe next time. We'll go through another one of these so you get the basic idea. All right, we'll stop there and we will see you next time. Yes.
Could I see the author?
Oh yeah, sure. This one?
Yeah.
Yeah, sure. Go for it. Yeah, no problem.
Can I also take?
Oh yeah, sure. Batch normalization. All right, I should